Hi, my name is Aastha Singh, and today I'll be talking about 5 manufacturing and design techniques that I find really interesting. So the 5 I'm going to be talking about are finite element analysis, PSPP maps, which I'll get to in a second, talk about what that acronym means, Ashby chart, eco-audit tools, and additive manufacturing. So a lot of these are going to be materials based, so like choosing a material for a design. So that is part of the design process, but that's kind of where my expertise lies, that's where my interests lie. And then the last one is something I have some experience with through my lab. So the first technique I have is finite element analysis. So essentially what an FEA software does is it takes a structure that you can create. Every time I've used FEA, I've created something in, say, SolidWorks or in Autodesk software. So you take it and then you apply different conditions like the temperature, loading conditions, movement, stuff like that. And then the software is going to tell you how this object is going to react to it. So engineers can use this to find areas of improvement or potential failure points and sort of beef those up before sending their product off to be manufactured. And what this does is it cuts down on the need to prototype models, which saves a lot of time and a lot of energy. So designs can be a lot better right off the bat instead of having to wait. So FEA is really great because it can test designs on your laptop or your computer without spending a lot of time and money. And it's very quick and you can change the conditions really easily. So within like 5 to 10 minutes, you can take a model and you can test it in a bunch of different conditions. And that makes it really, really easy to see how a model will react instead of having to manufacture it and then actually test it, which is very time consuming and very expensive. However, FEA is not perfect. It is a model, and all models have some degree of inaccuracy. So the accuracy of the model depends first on the skill of the engineer, how well they know the loading conditions, how well they pay attention to the detail, like the room temperature, the attachment points, the boundary conditions, stuff like that. And like I said, it is a model, so it only offers an approximate solution. Testing it in real life may yield some results that were kind of unexpected. So it's a good starting point, but it should never be like the final point. And this is used in somewhere like places where it would be very, very important to have structurally integritous objects, and places usually where making those objects is very costly or time consuming. Like when you're designing a bridge, you can't really prototype a whole bridge. So it's really, really important that we use these models to be able to test the safety of the bridge. Same thing for designing automotive parts, aircraft, anything that needs to be really, really safe and is very, very big. So this is a PSPP map, which stands for Processing, Structure, Properties, and Performance. Basically what it does is it takes the manufacturing and composition techniques used to create a material, and then it shows how that impacts the structure of the material, which in turn impacts the properties that the material has, which then impacts the performance. This is really, really important for choosing materials for a very specific purpose. So you see how you have to manufacture and process that material to get the properties or performance desired. This provides a really nice comprehensive view of the entire materials processing system. So instead of just taking a material as it is, you can see how changing it would change the performance of the material. And so that can be used to inform design decisions and material design decisions, especially when creating a product. So this tool is really great for failure analysis. So if your material fails, if your design fails, you can sort of trace back to what processing techniques or what structures were important to that failure or preventing that failure, and then you can sort of improve from there. However, sometimes materials don't always behave as predicted. There's always some degree of variability. While a PSPP map can give you a great overview of it, still testing has to be done. Sometimes you'll have to use a different material. And a PSPP map can only predict so much. There's always going to be factors that could be missed. So these maps are especially useful when you choose materials for really, really specific functions, such as semiconductors. Those have to have a very, very specific composition and structure to make sure that they function as intended. The next tool I'm going to talk about is something called an Ashby chart, and this is used to select materials with given constraints. So let's say you wanted to select a material that provides you the highest elastic modulus per unit density or the highest strength per unit cost. So wherever there's some sort of trade-off, you want a lower cost while maximizing how strong it is, that's where you would use an Ashby chart. So it plots different material properties, different combinations, different functions of material properties on both axes. Then you can use functions, formulas to get lines that will tell you where your ideal material would lie. And so this way of selecting material is very comprehensive because you get all your variables in there. It's very quick and it's very visual. So it's a really great tool to choose a material when you're making your design. And that in turn will, inform your design. And so you can choose materials that are energy efficient, that are cost effective, that are space effective, while maximizing performance. It's a very, very easy tool to use. I used this in one of my classes last semester. There are softwares that do this really beautifully. So ASPE charts are really great because they're very exact. Like I said, it's all mathematical. There's no guesswork involved. And you can juggle multiple constraints. You'll have different lines on your chart, which you can see in red, and then the one point, the one material that's closest to both lines, that's the best material to use. So that's all math, which is awesome. However, it depends on the application you're using. Sometimes a lot of them don't have the materials that you might be looking for. A lot of them are very limited. So your material selection process might be very limited just because of the constraints of the materials database. But yeah, it's still a really great tool to use. This can be beneficial to pretty much any industry, aerospace, automotive, biomedical, etc. Anywhere where material choice is a very integral part of the manufacturing process. All right, so next we have eco-audit tools, and these are usually softwares that can assess the environmental impact of different processing techniques, of different materials, and this is really, really important because nowadays we're trying to make manufacturing more eco-friendly, we're trying to make products more sustainable, make them last longer, trying to comply with all these different regulations, so it's a very, very important part of the manufacturing process. So tools like these can help designers measure these different metrics like carbon footprint and recyclability. Then as they make small changes to their design, small changes to the materials they use, they can see in real time how it impacts the eco-friendliness of their material. And so this in turn would help them make better, more informed decisions about their designs. So these tools are great because it's really, really easy to comply with environmental regulations when you have all the data, all the impact at your fingertips like this. However, the impact, the range of the software only extends so far. It really calculates only the big environmental impacts, but like pretty much every decision we make in manufacturing will impact the environment in some way, and this software may not be able to catch all of that, but it's still a great tool to use. And it can be used in industries that have to comply with environmental regulations, some of the most regulated being automotive and aerospace industries, right? Industries with a lot of waste and that produce, a lot of emissions, a lot of byproducts. This would really help with that. And so the final process or technique I'm going to talk about is additive manufacturing, specifically in regards to metal. So I am in a lab that deals with a lot of metal additive manufacturing. So the way this works is that a printer will take a melted metal and just create layers upon layers, building it up to create an object, or it'll have a bed of powder. It'll use a laser to fuse powder in select places, and it'll keep putting powder and keep fusing it together until it creates an object. So this creates a very customizable low waste part, right? With the powder, it can be reused, and with the filament, it only prints what it needs. So it's a lot more sustainable than, say, like subtractive manufacturing. And it can create some pretty high precision parts. If you look at the image shown here, that's a really precise part, and that was created using powder bed manufacturing. So it enables really complex part geometries, and it's great for rapid prototyping because once you have the model, you can pretty much just send it off and have the printer create whatever you want it to make. As I've said, This method is really great because it's customizable and it doesn't waste material. And if you need to make a part with like a lattice structure inside per se, you'd be able to do that because, like I said, it builds layer upon layer, so it can build outside and inside layers. It doesn't have to be just one uniform, density. However, because of the way this filament is printed, the part is usually weaker along where these print boundaries are. And it's also slower to build than, say, traditional manufacturing techniques. While the whole process might be faster, the actual build time is much slower. So there's companies like Boeing or General Electric, General Motors that are using this process to create some of their parts. So these were the sources that I used. And that is all. Thank you so much for listening.